from Hazin İnci, an application of offset-free linear quadratic optimal control. And as a third presentation, Chatterjee type cyclic contraction in soft metric spaces will be presented by Simge Öztunç. And as a final presentation, Idrissa Kayijuka, Gauss-related quadratic rule for highly oscillatory singular integrals having hypersingular type singularity. Before starting with the presentation, I would like to remind you that our presentation fixed to 15 minutes. Since it's a virtual meeting for the other presenter, we should pay attention to be on time, and we should complete our presentation within 15 minutes, including questions, answers, and comment parts. That's why I strictly recommend you to complete your presentation within 12 or 13 minutes, to left at least 2 minutes for question and answer part. Thank you for your patience and thank you for your attention. So let's start with the first presentation. Antony is here. Is Antony here? Can you hear me? Yes, I think Antony is here, but we cannot hear you, Antony.
Just a minute. Can you hear me now?
Yes, I can hear you now. Now it's your turn. Welcome. And please start your presentation.
Okay, good. What's the time right now, that side of the country? Good evening, everybody, and welcome for this presentation that I'm going to give a bit of characteristics. This work was a bit, it was disrupted due to Corona, so we will have the basic what we have done so far. Now, I'm going to talk about characterization of electrical power line communication, the channel and the impulsive noise. The outline of my work is introduction, a bit of it, a little bit of the background, the channel measurements, the noises in power line communication, and the conclusion. Now, what is power line communication system? Power line communication is just a system that has been there for many years. It's only that we are using the pre-existing electrical power line for transmission as a transmission media for our data. So in essence, I mean, we are going to be using, in the houses, for example, you already have cables that have already been installed. So we try to use those ones for communication purposes. The main reason behind this is because power line are the most, how can I say it, ambiguous power lines that are in the world. They're connecting almost every house, almost every part of the country. So that's why using it will be cheaper. We will be avoiding extra installations. Now, the introduction of this of power line started way back in early 19th century, when Edward Davy suggested a remote electricity metering system. Then it continued after some 50 years with Joseph Rotin and Brown, when they did the patent of the first signal electricity meter. Then the work, it elapsed a bit because of the challenges that are there in power line communication. So it had to wait until another extra years before Charlton did another patent on remote reading meter system. Then the work continued, and in the early 50s, there was a development of a simplex transmission over power line channel. Now, the reason why we are going to use, trying to study power line communication channel is because, one, it is cheap for the last mile solution. This, in essence, as I explained earlier, we have electricity lines almost going to every houses, and this is through statistic that is from World Bank, the World Bank statistics showing the world access to electricity. Almost all houses in the world, almost 90% by 2018 were connected to electricity. So this data, by now it should be higher. Even in countries in Africa, the number is going up. So that is one. It is cheap because houses are already connected to power line. However, the channel has a lot of noise. It's a very hazardous channel. That is one problem that we're going to face. The channel characterization has to be reliable for communication. So that's why there has to be study for this so that it's reliable for communication. The background, literally, this is what we'll talk about. Lines are divided in 3 sections. There is the low voltage side, which is connecting the houses. As you can see next to the house, there's the low voltage side. And then there is the distribution side, which is on the high voltage side, the powers where we have the standing antennas, the standing power station, power erections with the black stuff. And in another challenge is every time we try to connect like data, we have to be using a transformer to bypass. We have to use the couplers to bypass the transformer for transmission. So that's why we have that showing there. Then in the middle we have the medium voltage. The medium voltage, because we know from distribution side, the power has to be broken down. Then it goes a medium voltage zone, then we bring it down to low voltage, and then we take it to the houses using the transformers that we can see there. Now, these are the levels that I've just explained. The highest level is high voltage. That is the high voltage, which is 100 to 380 kilovolts. And then the medium voltage level, which is 10 to 30 kilovolts. And then the low voltage level, where we have the houses. In the US is fixed 110. Another characteristics of power line communication, which it's not written there, is we have a situation whereby normal electrical lines are used for low frequency transmission. Electricity is roughly 50 to 60 hertz, depending on where it is. In my country, it's 50. I believe in Turkey is also 50. In the US and some parts of Canada and Japan, it's 60 hertz. Now, for effective coupling, which, as you can see from the previous diagram, those couplers, the effective couplers, sometimes you have inductive or conductive coupling. Now, the power line communication system have been studied before. So the studies have shown that using OFDM and FEC are the best method of transmission. It tries to reduce the so-called impulsive noises that I'm going to talk about a bit. Now, in this work, it was disrupted, but we plan to use what we call Gaussian adaptive system, which will be used in the modulation part to try to reduce the effects of impulsive noises further. Literally, OFDM is a system whereby the spectrum is divided into smaller portions, and the bandwidth is such that the signals are transmitted in sine and cosinus. They're perpendicular to each other, they don't interfere, and that perpendicularity tends to reduce the effects of impulsive noise when they arrive at the receiver side. Now, power line communication is divided into 3. The first one is not used much, but the currently in use, we have the narrowband and then the broadband, and the broadband one. The characteristics are given there. We can see right now in my work, I'll be trying to use the broadband side and the frequency of around 30 megahertz to 250. Now, another challenge that has been there is electromagnetic compatibility, which have been studied to ensure that there is proper compatibility that does not, we don't reduce intolerable electromagnetic disturbances in any of the systems that is in the area. The studies have been done and classified differently, right from the international level and even the regional level, and they've been divided into different categories. So the standards regions, government that are doing this, organizations, international and region, we have ITU. This one is the Senelec is in the Europe, the FCC is in the US, IEEE is also in the US, IEC is from the Europe side. Now, proper standards regulate communication quality as well as the and cater for minimal or if not zero interference to human health. Now, power and communication can be modeled in different situations. We can use a method different, but in this case, we're using transmission line theory, whereby the cables, the lines are modeled in such a way that we have the setup in that manner, where we have resistance and inductors connected in that particular manner. And the equivalent formulas as given, we have the equation for the propagation, both going forward and backward for both voltage and current. We can also derive propagation constant and the impedance. Now, for us to measure the channel characteristics, we need to have a setup of this nature, where we have the NA is the network analyzer and the coupling circuit. Now, the coupler to protect the device that is connected, to protect and also to minimize the effect that electricity.
Anthony, I would like to inform you that you have last 5 minutes, actually last 4 minutes. Please try to be precise on time.
All right. Now, when you, because of the low frequency, we need to, our signal is supposed to be on a higher frequency side. So we have to implement coupling circuit of this number, of this character, where we have a high pass filter to ensure that we have our signal passing by, because electricity is at 50 hertz, which is the low frequency side. And we took the measurements of the cables and look at them. These are the measurements that are there. Now we have an effect of what is called multi-channel multipath problem, whereby where we have a signal going and forth and coming back, and they're interfering, and that is one of the major effects. It's very close to wireless communication. So that is the design there. This is from another paper that I was looking at, because mine was not able to be done at the right time because of the corona. Now you can see the attenuation there. That is the normal one without connections of any electrical parameters, but the other ones we have connections of parameters. So we have, it's not as normal as the other scenario of attenuation. Now, if you look at the channel response, it behaves like that when we have apparatus connected in the sockets. So there are two scenarios both in time domain and frequency domain. The noises, as I said earlier, they're like that. We have colored, narrow, periodic, and asynchronous, which are these are how they're divided. When to measure the noise, we use this setup. And these are the characteristics whereby you find that the maximum, the average of maximum and low is roughly, for the three of them, is roughly 105, minus 105, minus 89, and the other one is minus, if I can see, minus 0.8, roughly the average of how they behave. And this one is the impulsive noise, where the mean of it, which we were measuring, the mean is roughly, the maximum mean is 230. The standard deviation is 123 in millivolts, and the durations is roughly between 150 and 205 microseconds. So conclusion, in essence, I will be working with a robust adaptive distribution, Gaussian distribution, to try to design a modem that will be able to give me a gain of 10 dB additional 10 dB signal to noise ratio. Thank you.
I would like to thank you for your nice presentation. We are running out of time, but if there is any short question, still we can take the question. If there is any question, I think no. Thank you once again, Anthony.
Thank
Have
you.
a nice day.
Thank you.
Now I would like to invite Hazin İnci for his presentation, an application of offset-free linear quadratic optimal control. Is Hazin here?
Yes, I'm here.
Okay, please go ahead and keep in mind that you have in total 15 minutes. Try to be on time and use your time effectively, please.
Okay, thank you very much. Is my screen available now?
Yes, it is. We can see.
Okay. Sorry. Okay, my name is Hazin İnci. I'm doing PhD in Ege University at Electrical and Electronics Engineering. We prepared this study with Professor Musa Alcı and Professor Aydoğan Savran, which our study is an application of offset-free linear quadratic optimal control. First of all, I will try to explain what is our problem and how we solve that problem in introduction section. And I will try to give a brief explanation about our experimental setups that we used as a real systems. And I will try to explain the problem formulation and which method that we used. And in experimental studies section, I will try to show you the results that we get, and we will conclude this presentation after that. In this study, actually, we used ball beam system and rotary inverted pendulum systems with linear quadratic optimal control, which we say LQR control. Main problem here is to make those systems to track a reference without any steady state error, which means that there will be no offset between reference signal and the output signal. We faced a problem while designing controller according to a linear model of those systems, and those linear model has already integrated. While we design those controller, we had poor controlling with those systems in real time. And then we solved that problem to augment this system with an integrator. And therefore, we solved the problem of the steady state error while tracking the reference. And later on, I will show you the results. So our experimental setups, first is ball beam system. Okay, which you can see here. There is a DC motor inside of here behind those gears, and this is the beam, and we try to control the position of this ball by using that DC motor. This arm goes up and down, and then that ball goes towards left and right. And this is a kind of like miniature of a crane system, but this is a laboratory setup so that we can use our method on this platform. I will not go into detail about nonlinear equation of motions of this system. It is already given by the firm, which is Quadrature. So I will go directly into the linear model of this system. As you can see here, the servo voltage to ball displacement transfer function is this. This is the ball displacement, and this is the servo voltage signal. As you can see, there is integrator already here in the linear model of this system. And we chose the system states as this, which is theta angle. That angle is the angle between gear and this arm. This is here. and the X state is the position of the ball. A linear model in state space representation, we can show it like this, generally, and the state space matrices are like this. When we check the controllability of this system, I mean, if this is a controllable system, by using this formula, we can say that the rank of M is full. That means this system is completely state controllable around operating points. With operating points, I mean that theta can work like 30 degrees and minus 30 degrees, etc. So within this range, this system is controllable. And for the rotary inverted pendulum, we use same from Quansar firm, this system. Our aim is to invert this pendulum and make it to track a reference, which is theta. So our system will track a theta, which means that rotary arm, this rotary arm goes to right and left within 30 degrees, and our pendulum will be inverted. The states are theta and alpha. Theta is rotary arm, and alpha is angle between that z-axis and the pendulum. And the pendulum angle is defined as with this formula, because before starting controlling this system, the pendulum is downward, because we have incremental encoder here. So it will begin with 0. At the beginning, alpha will be 0, so minus pi will be its degree of alpha, and then we will take the pendulum and invert it to a range of operating points, and then the controller will take the lead, and then it will control the system. Alpha equals to 0 means the pendulum is perfectly upright, and the model of this system related to theta, rotary arm angle, is this. As you can see, again, like ball beam system, we have integrated already here. States of the system defined as this. Theta is rotary arm angle and alpha is pendulum angle, and we have those matrices. Controllability matrix also checked for this system, and rank is full. That means the system is state controllable around operating points. So we use LQR method, which is an optimal control technique, and it uses full state feedback. For this control method, systems must be controllable and states must be measurable and observable. Sometimes we cannot measure some states, so that we can design observers to have measurements of those states. LQR basically minimizes this cost function. To minimize this cost function, calculates the control input u, and that u is minus kx, and that k must be calculated. The computation of that optimal gain can be calculated through this. We know R, we know B from there, but we have to calculate P, and that P can be calculated with steady state Riccati equation, which is this, and that P is positive definite matrix. I mean, actually, Q and R are the penalized matrices for the states. Q is for the states and R for the control inputs. So there are some methods to define those matrices. I will get to that later. In this study, we are not using actually LQR. R means regulator. We will not use LQR for regulating these systems. We will make it use to track a reference. So a non-zero reference is desired, then the control signal will be like this. So we have this K1R, that R is reference signal. And K1 is selected because our output signal is the first state. If it was second state, then it will be K2. And the calculation of K is not changed, it is same given formally. To deal with steady state error, I said formally, we will have steady state error if we design the system like this without any integral action adding. So we will have problem with that, but to solve that problem, we changed the control system structure like this to adding integral action here on the feed-forward path. So that integral term eliminates steady-state error. We will see in the results. Those error occurs due to constant disturbances and model mismatches. After adding this term, our model will be changed again like this. Actually, the structure stays same, but the matrices are changed due to additional state because of the integrator. And that K for the integrator comes after calculation of the K vector. Okay, I will show you the results. Firstly, this is the result without any integral action. As you can see from the right path, position of the ball, try to control that the reference is the with the color of pink. This is the reference, and in simulation you can see that it tracks the reference perfectly. But in real system we have offset between the reference signal and the output signal. That red one is the real system, and in the error figure we can see that there is a steady-state error here. Actually, in simulation, we use nonlinear model of the system, and we applied white noise in the simulation, and we applied disturbance.
Hazin, I would like to inform you that you have 5 minutes left. Please try to use your time as much as effective you can. Okay, thank you. And let me go ahead with the other results. After adding integral action to the LQR control, as you can see, as a red signal, which is the real system result, there is no steady-state error here. We don't have any offset, so we control the ball beam system. We control the position of the ball quite good. And for the rotary inverted pendulum, at right side of the presentation, you can see alpha nearest to 0. That means our pendulum is inverted. This is the figure of the alpha. And on the left-hand side, we can see without any integral action, we cannot track the reference for rotary arm angle. We have offset here, as you can see. But after adding integral action to the control structure, the pendulum is inverted, as you can see here, which is alpha is 0. That means the pendulum is upright. And the reference of theta is tracked by the controller, and the error signal is 0, as you can see, the mean of it, I mean. So as a conclusion, considering the integrator of the linear model and trying to control those systems with conventional LQM method gives us poor tracking results, and the issue with steady-state error is solved by augmenting the system with an integrator, by adding that integrator in the control system. From the result, we can see that from the result of real system application, mathematical models are approximately representing the actual plants even for the laboratory setups. So the revisions may be required for the controllers before applying to the actual plants. And by the way, for different aims, penalizing matrices Q and R could be changed as well. In our study, we selected Q and R as unity matrices, but it can be changed. For example, the weight of relevant state, which is desired to track a reference, could be increased for faster tracking. And on the other hand, R could be increased for lesser control effort. Thank you for listening. I can take any question if there are any. Thank you. Thank you for your nice presentation. If there is any question. No, thank you. Now, I'd like to make a little bit funnier this session. My son is 2 years old at home watching me through YouTube. So I'd like to say hi to him. Hi, Kerem. Hi, Kerem. And for the next presentation, I would like to invite Simge Öztunç. Is she here around? If not, I'm going to continue with Idrissa Kayijuka, Gauss-related quadratic role for highly oscillatory singular integrals having hypersingular type singularity. If Idrissa here?
Yes, I'm here.
Welcome. Please
Thank
go
you.
ahead with your presentation.
Yes, let me share first. Are you seeing my PowerPoint presentation? Are you seeing my PowerPoint presentation?
Yes, you can use, you are allowed to use. You can share the screen.
Yeah, I have shared the screen. I would like to know if you are seeing it.
Yeah, it is available. We see that.
Okay, thank you so much. Okay, thank you so much. Good evening, everyone. My name is Idrissa Kayijuka. I'm a graduate student from Ege University, Department of Mathematics. Today, I would like to present my paper with the title Gauss-related quadrature rule for highly oscillatory integral, singular integrals having hypersingular type singularities. As an abstract, hypersingular integral equation, they arise in many engineering mechanics problems, such as plasticity, the aerodynamics of light vehicles, elasticity, and modeling of aircraft vortex works. In this paper, Gauss-related quadrature rule of highly oscillatory singular integrals with hypersingular kernel singularity, they will be investigated. The original integral here is going to be transformed into the sum of several line integral on a positive semi-infinite integral. It means from 0 to infinity. Then since some of the integrals contain logarithm complex integrand, those type of integral complex integrand, they cannot be computed directly. There will be some modification. Among some modifications, it means we'll use Gauss method in order to compute them efficiently. The method utilized here is based on the moment information. It means we'll use modified moments, Chebyshev and its modification algorithm. Here, the recursion coefficient of three-term recurrent solution that satisfies orthogonal polynomial with respect to the convention generalized Ragel polynomial and Cauchy logarithm weight functions, they will be discussed. Finally, we'll give some numerical experience to show the effectiveness of the proposed algorithm. The keywords to be used here, they are oscillatory integrals, Gauss quadrature rule, orthogonal polynomials, of course, hypersingular integrals. So as an overview of this type of integrals, we will use two types of singular integrals. There will be logarithmic integrals. Let me try to use the laser point here. Okay, there will be logarithmic singular integrals and as well as the algebraic singular integrals. These logarithmic singular integrals have numerous applications regarding wave scattering in strip diffraction problems, aero and hydroacoustic problems of the theory of elasticity. You can check here, I have given some references and so on. For hypersingular integrals, they play a vital role in physics and applied mechanics, where they can be utilized to formulate mixed boundary value problems. Besides those, we may also find several applications of finite part integrals, or they are called Hadamard finite part, in electrodynamics, aerodynamics, acoustic, and so on. For the reader, we can refer the reader to check for the reference 428. The BEM, boundary element method, are the popular method nowadays for handling partial differential equations involving the integral with singular kernel functions. However, when the kernel functions are simultaneously singular and highly oscillatory, some traditional numerical methods, they fail to approximate those type of integrals. So there will be three kinds of singularity will be arised. Some will be weak, strong singularity. They are known by Cauchy principal parts singularities. There will be also hypersingularity, which are our topic today. In this paper, our central interest is the computation of this type of singular integrals, hypersingular integrals. As you can see, this is what we call algebraic singularities. This is the logarithmic singularities. It means when this S is 0, it means we remain only with algebraic singularities. When S is 1, we will have algebraic singularity as well as logarithmic singularities. In the denominator here, we are having the value mu. This mu is the value between our interval of integration AB, and this one, it is what we call Cauchy singularities, or it will be Cauchy singularity when k is equal to 0, and when k is greater to 0, it will be hypersingular integral. The function here to be taken, we will assume, since we are going to integrate in complex region, it means we assume our function to be analytic function in an appropriate large region containing our interval of integration. But here you can see e power I omega x is our oscillatory factor. The omega here, it is what we call frequency. So once the frequency becomes large, this integral becomes very difficult to compute. That's our aim today. For the simplicity, we can take this algebraic and as well as logarithmic singularity to be abbreviated by omega alpha beta s x times our analytic function times the oscillatory factor divided by our Cauchy singularity or hypersingularities. As we can continue, if we analyze this integral 1, when s is equal to 0 or 1, as I have said, our integral will be algebraic or logarithmic high oscillatory integral. If we check when k is equal to 1 here, we will have Cauchy integral, Cauchy principal value. If k is equal to 2, our integral will be Hadamard finite integral. When k is greater or equal to 2, our integral will become hypersingular oscillatory integrals. Based on this, on the assumption that we have already mentioned that our function is analytic and appropriate closed large region containing the interval of integration AB, our original integral will be transformed into several line integral in a positive semi-infinite interval. Subsequently, those line integral will be computed using Gauss-related quadrature rule. Furthermore, algorithm to produce those recurrence coefficients of 3-term recurrence relation that satisfy an orthogonal polynomial with respect to Gauss logarithmic weight function over the positive half infinite integral will be also compared by using the moment information approach. Finally, the numerical experiments will also given to show the effectiveness of the developed method. As I have said before, we will compute our integral using a closed complex region. Like as you can see, the integral will be drawn in this closed region. So it means using the Cauchy integral, because using the Cauchy-Gurchatz integral theorem, which says when our function is analytic in the region R on its boundary gamma, then the sum of closed integral will be equal to 0. This is the main theorem to be used here in order to compute that type of integral. So
I would like to inform you that last 5 minutes, please try to be on your time.
Yes, let me try to summarize what I have written. So I was explaining that this integral will be, we are going to calculate this integral. So it means if we will take the sum of all line integrals and the sum of this one equal to 0. If we equate equal to 0, we can directly get our line integrals. So this is our bounded gamma. You can see that we have already calculated it. If we use this theorem, when we assume that f is analytic in a simply connected curve, the integral will be represented by this formula. So where this IA will be given like this one and this one will be given like this one. I won't read too much because we have limited time. So as we can continue, the proof of this theorem will be given in the full paper, but the line integrals here will also computed by Gauss quadrature rule. By computing the Gauss quadrature rule, the above integral can be simplified as this one, where all of these expression J1, F1 are given below. So after this one, we will use Gauchy analysis, where we compute logarithm complex function like this one will be transformed like this one, and the above integral will be written in this way. It means here we are going to have like weight functions. You can see those are Laguerre weight function. Those are Gauchy logarithmic Laguerre functions. Weight function I have already given to this one. So it means our problem here will be only to be write the above integral in this way. The remaining problem will be to find these weight points and nodes, the abscissas. As we all know, our nodes here, we have already calculated them using a program written in Mathematica. Here we took alpha to be -1/4. We took the precision of 60, and the arithmetic digit we used 32. The computation here used was 0.01562625. Those are nodes. Since we have the nodes, and we all know that the nodes, they are the eigenvalue of Jacobi matrix, and the weight, since we have the weight can be calculated in this way. The numerical example here, I have chosen to give only like one example here to compute one example since we don't have time. The example here, we will take our integral from -1 to 1, and we will take the function to be a trigonometric function sine. Here, the integral to be computed is finite part. The integral is called Hadamard finite part, highly oscillatory integrals. The alpha here was taken like this, beta was taken like this, and mu is equal to 0. Here we can see that we choose several values of omega. Omega, as I have told you, is the frequencies. As you can see, if we find the absolute error if I can remind you, the absolute error is the magnitude difference between the exact solution and the approximated one. We can see that when omega is equal to 10, yes, thank you.
1 minute left. Please try to complete your presentation and cover your presentation.
Thank you. I'm actually draw the conclusion here. My conclusion, it means our method was found to be efficient, since we can see that if we find the absolute error for omega increases, also our absolute error also will increase, will be -23. And we can see that our computation time also is small compared to the current methods. Thank you so much. I have given some references. For more about this paper, I think we will share the full paper. Thank you so much for the attention.
Thank you very much. With this last presentation, we complete this session, and as well as we complete this symposium for 2020, the 4th International Student Science Congress for this hall for session 22 is ended. So briefly, I would like to say several words, and I would like to invite you to the upcoming year's annual symposiums, because this symposium is held each year. Hopefully, we are planning to continue with the 5th International Student Science Symposium for 2021. So once again, I would like to thank you for your presentations. I would like to thank you for your participations. I would like to thank you for your patience and for your understanding. Because at the beginning, as an organizing committee member, we planned to carry out this symposium as an oral presentation face-to-face. Due to the pandemic situation, due to the COVID-19 pandemics, we decided to be held here, maybe a little bit far away from each other, maybe in front of the PC, maybe through the camera and the microphone, but at least to continue with our symposium. Hopefully you enjoyed, hopefully you liked our presentations, hopefully you got enough scientific data and what you are looking for. We will be glad to host you in upcoming year's symposium. If there is any inconvenience, please forgive us. Please let us know what's missing, and thank you for everything.